Alright, this screencast is going to be about our basic mole to mole and mole to mass, what's called stoichiometry conversions. And the word stoichiometry can sound a little scary, but really all it means is the mass and mole relationships between reactants and products. So if you think about a balanced chemical equation, we have reactants on the left and they form products on the right. And so we have to balance these chemical equations because the law of conservation of mass says that we can't create or destroy atoms. So we come in and we add coefficients out in front, and those coefficients actually become our mole ratios. They do not become our mass ratios because everything has a different molar mass from the periodic table. So if we were to look at this first balanced chemical equation, we've got C6H12O6, and there's an understood 1 out in front of it, which means if we had 1 mole of this, we're going to form 2 moles of CO2 and 2 moles of C2H5OH. So we can do mole conversions. We can say, well, if for every 1 mole of this, we would make 2 moles of that. Or let's say we had 2 moles of the reactant, then we can make double that, or 4 moles of CO2. So this first question says, well, if we wanted to produce 5 moles of CO2, how many moles of glucose, which is this guy, would you need to do that? And so you notice that our given goes in this top spot, and then we want to make sure that we're writing what it is. It's a pain, I know, to write out moles of blah, blah, blah. But if we do that, we can make sure that we get our mole ratio in the correct spot. So we want to know the relationship between these two. And to find the relationship, you look at the balanced chemical equation. Well, we said for every 1 mole of C6H12O6, so that's going to go there, we're going to make 2 moles of CO2. So this is a 1 to 2 mole ratio. So if we are given 5 moles, then we'll divide by 2, multiply by 1, and we get 2.5 moles of the glucose. So that's just doing a mole to mole, and that's taking the coefficients to do it. So if we wanted to go an additional step and find grams, it really is just one additional step. The way the notes lay this out is in a 2-step process. Sometimes this makes more sense to students than doing it in a long bridge. So we'll do it this way first, and then I'll show you how you do it as a long bridge. So here it says how many grams of glucose. So this is still our question mark, but instead of moles, they want grams. And if you think back to when we did conversions, we have mole mountain, so we've got moles up here, grams here, and particles here. And so if we want to convert from grams to moles or moles to grams, we use the atomic mass, which is grams per mole, right? Over here is where we need Avogadro's number, and we're not on this side of the mountain right now. We're over here. All right, so in order to get from CO2 to glucose, and before I can even bring grams into it, I've got to figure out what their mole relationship is. And we just did that. We said there 2 moles of CO2 would be formed for every 1 mole that reacted. So we end up with 4.0 moles of glucose. But that's not what the question was asking. The question was asking, well, how many grams of glucose would that be? So then our second bridge, we take this given and plop it in the top spot. And what is the true conversion for 1 mole of C6H12O6? And if you think back to when we did molar masses, we go to the periodic table. So for C6H12O6, we're going to do 6 times 12.0, because that's the mass of carbon on the periodic table, plus 12 times 1.0, because that's the mass of hydrogen, and then 6 times 16, because that's the mass of oxygen. And if we add that all up, and remember we're going to take our molar masses always to 1 decimal place. That way our sig figs will match, because we could certainly carry more decimals. Lots of periodic tables give you 4 and 5 decimals. For what we're doing, 1 decimal is fine. And so we're going to take that 180 grams, and what this conversion means is there's 180 grams of glucose in 1 mole. So if there's an understood 1 there, then I put 180 grams up here. Now sometimes students ask, well, what if there was a 2 in front of that glucose up here? Would I then put a 2 here? And the answer is no, because you want to think about these conversions to be true, right? So if we say there are 24 hours in 1 day, that's a true statement. It would not be correct to say that there are 48 hours in 1 day. But if we wanted to, we could say there's 48 hours in 2 days. But all we're doing there is multiplying. So if if this had a coefficient of 2 and you used it, then to make this true, you would have to double that molar mass. We just don't want to do that. So when we do molar masses, they're always going to be per 1 mole. All right, so we multiply those guys together, we get 720 grams. So that's certainly one way that you could do this problem. Another way that some students like it a little bit better is to just do it all in one bridge. So let me show you that out to the side. So our given is 8 moles of CO2, and I'm trying to get to grams of glucose. So again, moles of CO2 are here, so I'm going to put moles of CO2 down, moles of glucose up, and the relationship is 1 to 2. And then rather than stopping, getting a number, and doing another bridge, I could just say, okay, well, 1 mole of glucose, I want that to cancel, and I want to get a mass. And the molar mass is 180.0. So this does it all in one bridge, and you end up getting the exact same answer. So either way is fine. Our bridges are going to continue to get longer and longer. So I would recommend doing it in one bridge, but if this makes sense as we're starting, you're more than welcome to do it that way. All right. So at the bottom, we've got some practice. They've given us kind of a skeleton equation, and you know, they haven't balanced them. Sometimes I'll say, using the following unbalanced equation, and students think, oh, she wants me to use an unbalanced equation. No, I never want you to use an unbalanced equation. I'm trying to let you know, hey, this equation is not balanced, so get it balanced before you try to use it. So we'll come in, we'll make the oxygens even. That gives us 4 hydrogens, and then we'll put a 2 there. So it says, how many moles of O2, so this is our question mark, and they want moles, would be needed to react completely with 3.7 moles of hydrogen. So it's a mole-to-mole conversion, and in order to do that, I need the coefficients, and there they are. So 3.7 moles of hydrogen is the given. Moles of hydrogen is up top, so in order to go away, it's going to go on the bottom, so moles of hydrogen. And then up top, I want moles of O2. Well, how do you get a mole-to-mole relationship? That just comes from the balanced chemical equation. So this reaction says, for every 2 moles of hydrogen, you need 1 mole of oxygen to make 2 moles of water. It's not asking anything about water. Our relationship between oxygen and hydrogen is 1 to 2. So I'm going to say 3.7 times 1 divided by 2. And with 2 sig figs, my final answer is 1.9 moles of O2. All right, next question. How many grams of CO2, they want this in grams, would be produced if we started with 5 moles of O2? All right, again, this reaction's unbalanced. So this is a combustion reaction, and the easiest way to balance combustion reactions is alphabetically. So C, then H, then O. And if you end up with an odd number of oxygens, that's not going to work with an O2, so then you just come through and double everybody. All right, so carbons are fine, hydrogens are not fine, so I need a 2 there. And then make sure you count your oxygens in both places. We've got 2 there and 2 more, so that's a grand total of 4 on the right, so I need a 2 there. All right, so now that it's balanced, I can use it. My given was 5 moles of O2. Moles of O2 we know has to go down. Go back to the question. It says, how many grams of CO2? So I need the relationship between these two guys. Well, for every 2 moles of O2, I'm going to make 1 mole of CO2. So the 2 goes with the moles of O2, and then 1 mole of CO2 goes up top. All right, I could stop here, or I could keep going. They want grams. So if moles of CO2 are here, I'm close. Moles of CO2 have to go down, and grams go up. Well, where does a gram to mole relationship come from? Mole mountain. If we have moles, we have mass, we got to use the grams per mole conversion. So for every 1 mole of CO2, the molar mass is 44.0. So that comes from 2 oxygens, which is 32 grams, plus 12, which is carbon's mass, and you get 44. So we'll do 5 times 1 times 44, divide by 2. Final answer with 2 sig figs comes out to 110 grams of CO2. So that would be your final answer for that one. All right. Number 3 says, using the reaction from number 2, so this same equation up here, if 0.56 moles of water was produced, then how many grams of methane were burned? Now, if you're looking at this equation, you're like, well, who in the world is methane? First of all, you know it has to be a reactant, right? And you know that that's oxygen, so it's here. You also know every other thing. You guys know that that's water, you know that that's CO2, that's oxygen. So this is methane. That's who they're asking about. The given is in terms of water. So if I have 0.56 moles of water and I'm trying to get back to my methane, what is their relationship? Well, if 2 moles of water were produced, then it took 1 mole to do it. We have this number, right? So I know moles of water is going to go down. Moles of CH4 is going to go up. Their relationship is 1 to 2. So now I've canceled my waters. I've got moles of CH4. My last step is to get this into a mass. So 1 mole of CH4, I need to find the mass, and that comes from molar mass. And so 1 carbon is 12, 4 hydrogens is 4, so that molar mass is 16 grams per mole, and we get 4.5 grams of CH4 as our final answer. So that's how those work, and we've done mole to mole and mole to mass. And right here now you've got additional practice. This on the back side is just saying, well, what are the mole relationships if you're given this balanced chemical equation? So if I were to do C4H10, I take his coefficient, it's a 2, and then oxygen's coefficient is 13. So these become your mole ratios. I know in math class, if you had, something like this, like 2 over 10, your math teacher flips out if you don't reduce that to 1 over 5. Know that you're welcome to use that, right? I would much rather you use 2 to 10 than like to incorrectly reduce this to like 1 over 4 or something. So it's totally fine to leave these numbers unsimplified within your bridge. So that's all that question is asking for. So if you want to pause the screencast and go ahead and work out 2, 3, 4, and 5, go ahead and do that. I'm going to go through and write the reactions and the answers out so that you can check your work. So feel free to pause this so you have time to practice, and then you can score your own work when you come back. All right, so number 2 balanced, 2 yields 2, 3. And there were 2 questions here. So your first answer is 18 moles of O2, and your second answer is 576 grams of O2. For number 3, you had to write the entire equation out. So 5O2 yields 3CO2 plus 4H2O. And again, you had 2 questions. So the first answer is 20 moles of O2, and your second is 290 grams of, I believe that was water. All right, number 4, the balanced chemical equation. This is a synthesis reaction. You've got 2 elements that are forming a compound. There's your balanced equation. This answer was 3.00 moles of CH4. This one was 48.0 grams of CH4. And then for the last one, number 5, your balanced chemical equation, Na plus O2 makes Na2O. Don't forget to balance those charges on the ionic compound. Sodium is +1, oxygen's -2. And then we got to balance the equation as well. So this is also a synthesis reaction. And your final answer on this one is 155 grams of Na2O. So if you did well on this particular task, moles to moles and moles to grams, feel free to move on to the next section. It gets into a little bit more grams to grams and more reaction writing as well.